Last year, Stripe processed $1 trillion in payment volume while maintaining an uptime of 99.999%. Infrastructure reliability requires operating a perfectly stable system. The foundation of that system is DocDB. It's an in-house database as a service built on top of MongoDB, and it handles over 5 million queries per second across more than 2,000 database shards. But operating a static, perfectly stable database creates an operational paradox. To keep hardware utilization efficient and to enforce strict isolation between major tenants, engineers need to constantly split and merge those database shards. That means continuously moving petabytes of stateful data across the network. There is a strict mathematical boundary for moving that data. Data migration cannot block incoming traffic for longer than a product application's standard retry budget. If a database takes longer than 2 seconds to accept a write, queries fail and the system drops payments. Traffic flows from the product application into a DO-based proxy server sitting above the DocDB shards. To process queries, the proxy references the chunk metadata service, a lookup table mapping chunks to physical shards. Achieving zero downtime at this scale requires decoupling the bulk transfer of data from real-time state changes. Stripe executes this through a strict 6-step data movement protocol. Step 1 begins when the platform's coordinator component registers an intent in the chunk metadata service. It explicitly maps out a plan to move a specific chunk of data from a heavily loaded source shard to a target shard. Step 2 requires taking a point-in-time snapshot of the source data, denoted as time t, to begin the bulk data import onto the target. Engineers quickly encountered a physical limitation here. Pushing bulk data onto the target shard using standard batch writes severely bottlenecked physical write throughput. This diagram of a B-tree data structure explains why. DocDB stores records inside a B-tree. Ingesting a bulk snapshot scatters incoming data randomly across the index, thrashing the physical disk. By sorting the payload first, data streams sequentially, maximizing continuous block write proximity. This single sorting optimization boosted bulk write throughput by 10 times. It allowed Stripe to complete multi-terabyte migrations within the operational timeframes required for production shards. By the time the snapshot finishes loading onto the target shard, the data is already out of date. Live user queries continued to mutate the source shard data after time t. Stripe's change data capture pipeline bridges this gap. Every real-time write on the source shard generates an oplog event. The system transports this oplog to Kafka, an external stream, and an S3 archive. The target shard then pulls from Kafka to execute delayed writes. Routing replication through an external stream ensures the migration doesn't consume the source shard's read throughput, which is needed for live user queries. Because this replication happens bidirectionally, it creates an edge case risk. A copied write could return to the source, catching the system in an infinite replication loop. The replication service avoids cyclical replication by applying metadata tags to its writes. This tagging also provides a way to revert traffic back if the target shard becomes unavailable. Step 4 verifies data correctness. The system compares asynchronous point-in-time snapshots of the source and target shards to confirm completeness. By isolating the migration through the change data capture pipeline, the system mirrors the database state while preserving the compute resources needed for active user transactions. Phase 5 is the traffic switch, the point where the actual transition occurs. Updating network routes while thousands of queries are actively in flight risks data corruption or dropped payments. Stripe manages this transition using a custom MongoDB patch, enabling a protocol called versioned gating. This state machine maps the sequence. The coordinator bumps the source shard to version 2, rejecting incoming version 1 queries. Kafka drains final writes. The coordinator updates the metadata route, allowing the proxy to fetch and retry rejected requests on the target shard. This token-gated sequence executes in under 2 seconds. The system swaps the physical databases out from under thousands of active queries, hiding the transition inside the application's built-in retry budget. With traffic flowing normally, the process concludes. The platform deregisters the migration and drops the original data from the source shard to free up physical storage. Scaling this process up to a macro level allows Stripe to manage physical hardware across the fleet. This grid represents over 2,000 individual server nodes, with light blue blocks showing underutilized hardware. The platform enables bin packing, where small chunks of data spread across mostly empty servers are consolidated into fewer, fully utilized nodes. This consolidation reclaims computing power and storage space that would otherwise sit idle. In 2023, Stripe used this protocol to transparently migrate 1.5 petabytes of data, effectively reducing the total number of underlying DocDB shards by 75%. Future development is focused on automated heap management systems. These will use real-time traffic telemetry to dynamically scale and partition shards without manual intervention. Engineering a system layer with this level of flexibility allows the physical topology to be reshaped while maintaining the uptime required for global financial traffic.